Hi there and welcome. I'm Rebecca Weaver. I'm going to be looking at section 9.3 in our applied calculus class. We're looking at the evaluation of definite integrals. The definite integral is the integral from a to b of f of x dx, and we've been doing these. We just compute the antiderivative and evaluate it at b and subtract off the antiderivative evaluated at a, where that antiderivative f prime of x equals f of x. So let's look at evaluating these definite integrals. If we have something like the integral from 0 to 1 of 1 over the quantity 1 plus 2x all raised to the fourth dx, we're going to do substitution. So first let's let u equal 1 plus 2x. We'll take the derivative of both sides. So we'll have du equals 2 dx. We'll solve this for dx so that we can do our substitutions, and we'll get that the integral is 1 over u to the fourth times 1/2 du, which is this piece right here solved for dx and replaced. Then we'll simplify that integral by bringing that constant out front, and then we'll take that integral, we'll get u to the -3 all over -6 plus c. Then we need to back substitute, and that answer is just 1 plus 2x all raised to the -3 over -6 plus c. We need to do the evaluation of our limits from 0 to 1 by replacing our x with a 1. Evaluating that, replacing our x with a 0, evaluating that, and subtracting those. So this is that computation, and you will end up with 13 over 81. So for our change of limits rule, if we're going to do a change of limits, which sometimes we're going to want to do that, suppose the integral f of g of x times g prime of x dx is subjected to the substitution u equals g of x, so that the integral of f of g of x g prime of x dx becomes the integral of f of u du. That means we can't leave those limits as they are, so we're going to have to change those in terms of u, and they can't be in terms of x, because over here on the left they're in terms of x, so we change those to be in terms of u. So let's play. Example, we're going to evaluate using the change of limits rule, so we're going to do this, and we won't have to do we could solve it the same way we did it last time, or we could just do it this way where we change our limits of integration. So we do the exact same thing we did before. We're going to let u equal 1 plus 2x, and then we get our du equals 2 dx. Then, if x is 0, let's figure out what u is. All we do is we just replace whatever u is. We just replace our x with a 0, so u is 1. So when x is 0, u is 1. So in place of this bottom limit where x is 0, u is 1. Now we need to get what u is when x is 1. Just substitute into that equation. We get a 3. And now we can solve this exact same way that we did before, but instead we'll get 13 over 81, just a little quicker. If you don't like that, you don't have to do it that way. It's just another way to do it. So let's find the area of the shaded region. And we know that y equals negative x square root of 9 minus x squared. And we're going to do this from -3 to 3. So to find the area of the shaded region, we're going to have to integrate that given function. But we need to know what our limits of integration are going to be. Therefore, we must determine 3 x-intercepts of the function, because we need to do this in pieces. So we have our given function. We're going to figure out where y is 0 so we can get those x-intercepts. Just solving that with algebra, getting our different factors, we're going to get first x is 0, then x is going to be our positive -3. And so there are our limits of integration. Of course, we could kind of look at it and tell by looking at the graph, but There's how you would find them if you couldn't tell. Therefore, the leftmost region above the x-axis starts at x equals -3 and ends at x equals 0. The rightmost region below the x-axis starts at x equals 0 and ends at x equals 3. So to find the area in the shaded regions, we're going to use the following. We're going to do this in pieces. We're going to do this in the piece from -3 to 0 and then from 0 to 3. And we need to make sure that our answer is positive because we did see that that area was below and we need to add positive areas. So we just put the absolute value symbols on there, meaning if it's negative, make it positive at the end. So now let's find an antiderivative for both integrals. We're going to use u equals 9 minus x squared. Take the derivative of that. You'll get du is -2x dx. So we're going to plug all of that in. And look at how sweet this ends up. It's just the integral of 1/2 square root of u du. I can take that integral pretty easy. Very nice. When I do, I get 1/3 u to the 3/2 plus c. Substituting back, I get 1/3 times 9 minus x squared, all raised to the 3/2 plus c. So now let's solve for the area of this piece. We're going to do this from -3 to 0 and from 0 to 3. And notice that I'm making sure to get that, make those areas positive because this is in pieces. When I do perform those computations and plug in the -3 and the 0, I'm going to end up with, and this is just me doing the computation, plugging each of those in, I end up with 9 and a 9, which is 18. Really sweet. All right, so let's evaluate the integral from 1 to e of the natural log of x dx. To solve this integral, we're going to need to do integration by parts, and our calculations can be set up as follows. Choose your f, choose your g. My f is going to be the natural log of x. My g is going to be 1. I'm going to then take the derivative of f, that's 1/x, take the antiderivative of g, well, that's x. So let's set this up in our integration by parts formula, and we would get, we put down our f, so that's our x, put down our antiderivative. Oh, there's our f and there's our antiderivative. Sorry, when I look up there. Okay, so I swapped those around to make it look better. Sorry. Minus the integral of, and then I have my antiderivative, and then I have my derivative of f, all dx. Just simplifying that, I'm going to end up with x, natural log of x minus x plus c. Now I've got to evaluate it with the limits from 1 to e, just plugging those in. I'm going to end up with 0. All right, that's a nice answer. If you need any help, be sure and email me, rweaver10@alaska.edu. I have some other videos in there for you to watch. And hopefully, if you need any help after watching those, be sure and contact me. Have a fabulous day. Bye now.